blocks, etc., are maintained in Unix. So what I had discussed, that was a more generic one, where that concept is implemented in different ways in different operating systems, and it is wonderful to see how it is implemented in Unix, because that will give you a much more detailed understanding, and also it's a fantastic engineering um, for an operating system. Now today in our lecture, I'll um, talk about some fundamental topics. One is the two different modes of operating system execution. Let me first try the thing that we always try and sometimes we fail, sharing the screen. Have I shared entire screen? Yeah, entire screen. Sure. So can you see the white screen?
Yes, sir.
Yes, sir.
Okay. Okay. All right. So suppose we have got a situation where, let me take only one. What's that? I want to make it a little thicker. Let's say that there is only one CPU. It could be done through more than one CPU also. And there are two users, user 1 and user 2. And there is one printer. And maybe some other resource you can think of. Let's say the printer or uh, maybe a particular block of memory, whatever. Maybe the C compiler. All these are single. Now this person, the first person here, he has written a program which has got some computation where it says C assigned A plus B and then printf. Printf, whatever you do here, all right? Some printf. And I suppose that's the end of the program. And this person has also written another program where he has done something like x gets y plus z and printf x. Now suppose, let's make the thing a little complicated. Suppose C is an array. So C is basically an array and X is also an array. All right, so just not printing one particular variable, and might be the array size is 100 in both the cases. Now you see that there is only one CPU, and these two people, A and B, are sitting on two terminals, and they are executing their programs simultaneously. Now, when I say simultaneously, now here I'd like to have some interaction from you. When I say simultaneously, what do I mean? Does it mean that everything is being done at the same time? I want some feedback from you.
No, sir. It just means they submitted their programs at the same time.
No, not only that. They submitted the program at the same time or not, I really don't know as yet. But both of them are concurrently running. Now, this is a concept that you should understand. Please keep this picture in mind. I'll come back to this. Okay. Now, say one program, let's say program for A, it is running and it has started. That means in which state is it? When it is running, then it is in the execute state. Execution state. And when B is running, then B is also in the execution state. Now, how many CPUs I have? Only one CPU. So, can more than one programs run on the same CPU at the same time? No. Therefore, what is happening is actually, what are they doing? They are time sharing, right? Last time we had talked about this, that there is some time quantum. After that, say this one, A was executing here, it goes back to the ready queue, and B from the ready queue comes to the CPU. And this thing goes on. So say 5 millisecond each, and they are going on and on and on like that till they come to conclusion. Now, each of these, A and B, now let me use colors. Say A is denoted, A is being denoted by these statements, and B is being denoted by blue statements. Now, these statements, so when B is executing, then a blue statement is executing here. When A is executing, then a red statement is being executed in the CPU. Now suppose here, is it clear? Is this part clear? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. Now,
Yes, sir.
at this point, A wants to do a printf and B wants to also do a printf. Now, printf means printing, say, array of size 100 or 1000 will take some time. So, in the CPU, it will be there, right? In the CPU, either say the blue program has come first, and the blue program is trying to do the printing. Or maybe through the IO processor. Last time we had talked about the IO processor. For the sake of simplicity, the logic won't change. Suppose this rectangular block is in charge of printing. Now this printing is taking quite some time, right? Because 100 elements are to be printed. Now, in the meantime, 5 milliseconds has elapsed. Suppose this timeout that was there from here to here was 5 milliseconds. And so blue's printing stops and red's printing starts, right? So consequently on my printer, I'll have some red lines and some blue lines interspersed. That's not what I want, right? I don't want that. That is not what is desired. Is the problem clear? Yes
sir.
or no? Therefore, I must have some means of allocating this system resource. What was the system resource here? The system resource was the printer and also the CPU, of course, but right now the shared system resource was the printer, right? And that printer cannot be that shared because I've got only one printer. So whoever wants to print will have to utilize that printer. But at any particular point or at any particular phase of execution, I cannot allocate it to more than one simultaneously. So there should be some management somewhere. So here you see that when a program starts executing, let's see, I write one statement and you have to, I think the class is not very interactive today. Why? Suppose a program starts executing. The program starts executing. Then what happens? What do you mean by that? One by one. Anyone? I want to know where is Ritik Sureka?
Yes, sir.
So you tell me, when a program starts executing,
Sir, the
what
code
happens
is
first?
sir, the code is loaded into the memory.
The code is loaded in the primary memory, fine. And who loads that? Is loaded. का मतलब क्या है?
Sir, CPU.
CPU loads. CPU is not a program. There is a fundamental mistake. Why? How can CPU is just a box? I mean, it has some electronics. So who loads that? I mean, that a particular program is brought to the primary memory is done by whom? Sarfraz.
Yes, sir. Hello. Hello.
Tell me.
Yes, sir.
Yes. Tell me. I mean, when a program starts execute, your friend Ritik had said that, correctly said, that it comes to the primary memory.
Yes, sir.
The program is not to the primary memory. He used passive verse. I want to have it in the passive verse. Who brings the program to the primary memory?
Hello. So, what was the last
Yes.
statement that you said? So what was the last statement?
I just said that, so this is very fundamental. We have said a program starts executing. That means, let me bring the picture again. The program was in the secondary memory.
Yes, sir.
Some program P was in the secondary memory. And according to Ritik, it is brought to some location in the primary memory. Right. My question is, who brings it to the primary memory?
So the operating system.
Yes. A particular part of the operating system, which is the loader, brings
Yes, sir.
it
Yes, sir,
to
loader.
the primary memory. Yes. Brings it to the primary memory. Yes. Next, what happens? Hmm? Next, what happens?
Sir, the first instruction is loaded into the program counter.
The address of the
the
first
address
instruction
yes,
is
the
loaded
address
in
of the
the,
first instruction.
yes.
Sir.
Instruction is loaded in the program counter, right?
Yes, sir.
Now, so that is done, and the program P is executing. And when I say the program P is executing, just if you recall the earlier diagram, say the program P is the red program. So each of the red lines are being executed one after another, right? And in this way, it comes to the printf statement. And when it comes to the printf statement, suppose the program itself starts printing. And in the meanwhile, timeout occurs and the other program starts, the blue program starts, and it also comes in the printer. So there will be a problem if both the programs are executing the printf statement simultaneously. By simultaneous, I mean that this entire time span in which the red program is printing red P, red print, and then blueprint, then red print like that. Simultaneously means none of them have it started. It has not yet completed. Before its completion, this has also started. That is what I mean by simultaneously. All right. So both of them are doing some I/O in the I/O state at the same time. Actually, that is in the last class I had drawn the two states. One is the execute state, another was the I/O state. So simultaneously, both the programs, since they have not completed the I/O, both of them are in the I/O state, red and blue, and both of them can try to access the printer. Think of the situation that these two printers are two singers. Sorry, two processors are two singers. And I am the audience, and both of them have started singing two different songs in two different pitches at the same time. Now, at this, so it may turn out to be very unintelligible to me. Normally, when such situation, so what will you have to do? You will have to ask them to stop, or say, think of this, that there are two singers standing in the podium with two microphones in their hands. You have got the control of the microphones. Now both the microphones are on and both of them are singing. So that will be a cacophony, right, to the audience. Nothing is understood. So what would you as the program manager do? अरे बोलो भाई देवादित्य.
Yes, sir.
What
Sir,
do you do as a program manager?
Sir, can give a signal to the IO that
अरे कहाँ आयो है भाई?
while one
I am in an auditorium. You are not listening to what I was saying. I was in an auditorium, and there are two. I am sitting in the listeners, spectators, audience space, and there are two singers with two microphones in their hands. You have got the control of the microphones. Both of them start singing two different songs at the same time, and I am not being able to understand anything. What would you do as a program manager?
turn off one of the microphones.
Turn off one of the microphones. Now, when one singer would like to sing, both of them want to sing. So what will they do? What should they do?
Wait for to finish.
No one has started, bhai. Both of them are there, standing with their microphones. Don't think in a very complicated way. Very simple scenario. There is an auditorium. So two singers. Now whoever wants to sing, what will he or she do? What resource he or she needs to sing? What resource is needed?
Sir, the microphone.
Microphone. So what will they do?
One of them
Just now
microphone
you had
off, one of them will be turned on.
How do you know? Turned on means automatically. How do you know that they want to sing now?
Sir, they tell the means the program manager.
No. How will the program manager know that A wants to sing or B wants to sing or both of them wants to sing at the same time? How do you know?
So the program will tell.
Which program? Where is the program? It's It's a stage, two singers standing, you are the program manager sitting by the wings, and I am a sole listener sitting in the audience. Very simple case. Simple question. Nothing of computer science here. Right now, it's common sense. Dheeraj,
Yes, sir. Sir,
Bolo, take up the question.
yes, sir. Both of them will try to compete for the microphone, sir.
How again? How to compete? They will start boxing on the stage.
No, sir. Sir, whoever wants to
Then
sing, he will try to like express some kind of signal, like raise hand or something.
again, signal. The problem is, being a computer science student, you have stopped being a stopped being a normal human being. Arey, I want to have the power to my microphone, right?
Yes, sir.
Because the program manager Devaditto was shutting off the microphones. He was shutting off the microphone. Now I want to sing. What should I do? Whom
I'll
should I request?
I'll ask the program manager for the microphone, sir.
Yes, so I'll request Devaditto that I want to sing.
Yes, sir.
All right. And at that time, Dheeraj also says that he also wants to sing. Now, what will Devaditto do?
Sir, whoever comes first, he'll give it to him.
Suppose both of them have come at the same time. Both have raised hands.
Sir,
So Devaditto or the program manager will have to resolve the conflict in in the favor of one singer, right?
yes, sir.
Yes, sir.
So that's a common thing. The computer science and engineering for short stands, it is CAC. So mostly you will find it is a common sense engineering. All right. So here also, both the processes are my God, again, both the processes are trying to execute something, right? So both the processes are trying to execute something. Um, so both of them are in the user mode. That means both of them means the system, the computer system is now working in the user mode. Now, whenever, so process P1 and process P2 or singer 1, singer 2. Now, processes are doing the some works which they need, and for that they have got their access to the registers, they have got access to their own local memory, and they are being able to execute. So the entire system in a time shared mode is still in the user mode. All right. In the user mode, they are being time shared, and P1 and P2 are working in an interleaved manner. Now, at this point, P1 is making some request which can possibly, please listen to me carefully, which can possibly conflict with somebody else's request. Because both of them are asking for some shared resource. This XXX means some shared resource request. All right. Now, whenever such a request comes, then I have to fall back on Devaditya or the program manager. So I cannot simply start using this shared resource by myself. What I'll have to do, I'll have to send a request to the system for using the shared resource. And that request, now I'm talking in terms of operating system, that request will take me to a kernel mode. All right? That will take me to the kernel mode where Devaditya is sitting. All right? And he will look at the kernel program, will look at the validity of this request, whether this request can be granted to this program P1 or it will have to wait or whatever. Now suppose when P1, the single P1 has made a request to the kernel for getting access to the microphone, Devaditya or the kernel finds that another person, P2, is already singing. So what should Devaditya do?
Deny the permission, sir.
Sir, tell the other singer to wait.
This P2 to wait, right? Or P2 was doing, P1 should wait. Yes, right. P1 should wait. Unless P1 is a very high priority singer, that P2 can be stopped and P1 can be started. That's a special case, but right, you are right, that P1 should wait. And when P2 finishes, P1 will be allowed to sing, right? And when P1 is allowed to sing, then with that permission, it goes back to the user mode because P1 can only work in the user. So here it is request and here is a request grant. And here there are waits and everything, etc., many other things. Is this thing clear? So whenever there is a shared resource access, request for a shared resource access, then we'll have to move out from the, we means operating system, will move from the user mode to the kernel mode, and that will be through a request, and that request is nothing but a system call. All right. Now, and on, now here, this kernel has got many things. One of the components of kernel is, what's happening? One of the components of kernel is the device driver. So there are so many devices in the system, and each of them have got their own drivers. You know, when you install a printer in your system, you have to install a printer driver, isn't it? And unless that printer driver is accessible, you cannot get the print. Therefore, the kernel will allow access to the printer driver to some process, P1 or P2 at a time. So what is happening? Now let's come back to printing. So here was my program, say read A, read B, C assigned A, B, and I say printf whatever C. All right. Now this printf, now this entire thing was being executed. This was my program P1. This program was being executed in the which mode, user mode or kernel mode? Which mode it was being executed in? Ovirup Majumdar.
Yes, sir.
Yes, so in which mode? I don't know. I mean, I think you guys are opening the
User-
terminal and parallelly you are doing something else, keeping yourself in mute. And when you listen to your name, then only wake up.
User
We'll
mode,
keep that
sir.
wake up situation. Huh?
User mode.
Yes, Ovirup, tell me.
User mode.
Fantastic. So you are sleeping, but what you have done is a beauty. It's a sleeping beauty. So yes, user mode. Till now it was in the user mode. When it comes to printf, uh, when it comes to the printf, then obviously you understand it cannot carry on in the user mode. So this printf, which is in high level printf, will actually be translated to a different assembly code where the print function will be also there, and there will be a number of things which maybe later on Subroto can show you, and there will be some system call inserted here. So this printf is as if a procedure that is being enacted and which has got a system call with all sorts of parameters being put. So this system call will be equivalent to a kernel call. Now, how will the operating system know, or in the user mode, whenever this sort of statement comes, printf type of statement comes, then the operating system how will the operating system know? I was going to tell you a wrong thing. You see, when it is executing, who is executing? The OS or the program in the CPU?
The CPU.
Who is executing here? In the
sir.
CPU, who is executing? The program, user mode, right?
Yes.
Now, how does all of a sudden it occurred to us that here I could do read A, read B, C assigned A plus B, but for printf I'll have to make a system call. Who tells you that? It is being told, it is done in this way, that there are two types of instructions. There are two types of instructions. Some are privileged instructions. I think I've made a mistake in spelling. Instructions and non-privileged instructions. Or somebody say that it is a, yeah, okay. It's a privileged instruction and non-privileged instruction. Okay. Non-privileged instructions can execute in the user mode. But whenever a privileged instruction is encountered, now all of you know that any instruction A assigned, when I say C assigned A plus B, that is actually broken down into a number of machine level or assembly level operation, right? Say like, say read A, read B to here. So here, this addition and this assignment. Now this addition is equivalent to add, which is a assembly level instruction. Similarly, move, this assignment is nothing but a move instruction, assembly level, like that. Now, these instructions are instructions which can be executed in the user mode. But if there be something like in or out, say this sort of instructions, which are privileged instructions. Now, when the instructions being executed by the CPU, you remember, if you recall your organization architecture class, then before the thing comes to the CPU or the ALU, it comes to the instruction register, right? The instruction is fetched in the instruction register and that is decoded. You remember this small little diagram? Fetch, decode, yeah, fetch, then decode, then execute. You remember this? This was there in your computer organization. Any instruction executes in this way. Do you remember this? Yes or no?
Yes, sir.
Yes,
Yes, sir.
Yes, sir.
When this decoding is being done, look here. When this decoding is being done, I can very well understand. That means the hardware can understand that, oh, this is a code which is not in my jurisdiction. Therefore, immediately that the CPU will set a bit, a flag, a particular bit will be set to 1, which tells that now it is the job of the kernel, because this instruction has to be executed in the this is a privileged instruction and has to be executed in the privileged mode. As soon as that is done, this bit is set to 1, a sort of hardware interrupt takes place. And when this bit is 1, then I know that it is a system call, and so I come here and the system call is generated. What is a system call? Why was that bit set to 1? Why was that bit set to 1? That bit was set to 1 because it was a print instruction. It could be a file open, file close, it could be read, file, okay, it could be anything. So there could be n number of things. So depending on what service you want, you have got some parameter. All right. So the parameter here was print. So this is a system. So there is an interrupt that brought you here with a particular system call that is parameterized to printing. So now let us look at the kernel. So Mr. Kernel is, and a request has come with some parameter called P, means printing, say. So as soon as it comes, then you see here it is something like a gateway. There can be a number of processes, but whenever we want to go to some shared process, there is Devaditya sitting here, the resource manager. All right. Everybody will have to come through this gate. Everybody. And so there can be more requests coming. Request from blue, request from, say, another P request from blue, another P request from green, whatever, all these things can come. But the kernel is keeping a data structure to remember all these and is making a decision as to which process this should go. This request should be granted. Okay? And accordingly, yes, accordingly, the kernel will allow that particular process, in this case, the read process, to do the printing. And once that printing is completed, the kernel will again back to the user mode. All right. So the things are happening something like this, that I was in the user mode, and then there was a system call. I come to the kernel mode, provide the service, and go back. You can ask me, why, sir? Why are you are going back? P and Q, these requests were there with you. P, the green and the green and the blue requests were there with you. You just served the red. Why did you go back to the user? Why didn't you allow them? Can you tell me why? Can you tell me why? Anybody? Dhiraj?
Yes, sir. Uh, Sir, the resource was
Why?
sir, the resource was busy. I could not run them both.
No. Why did I go back? Because the time quantum was there for that process, right?
Oh, yes,
Since the
sir.
time quantum was there, yeah, so although the requests are there, it's not their turn. I have gone there, okay. Now I've gone back there. So now with the system call, I come to the kernel and uh, with on completion, I go back to the user mode. And whenever, suppose now, and another program, which is some program, maybe P1 itself, wants to do some work on some file, then for that you will see that there are some system calls like open, that means file open with some parameters. Whenever that sort of system call is encountered, that will again come to the kernel. The kernel will look at the file and we will open the file and allow, because if there be an open file and more than one process write on that, then that is not desirable, right? So I should allow any one to write. For reading, I can allow more than one, by the way. You see, here there is an interesting point, that suppose there is a file. There is a file. And more than one processes wants to read it. Can you allow them to read simultaneously? Yes or no?
Yes, sir, we can.
Yes, but if there be write, then we cannot. If one is read, another is write, then also we cannot. Isn't it?
Yes, sir.
That is rather tricky today. Subrata, you have to arrange for that Excel sheet of attendance, but that won't serve the purpose also, because they will give the attendance. I want to see also set the time, how long they are in the class, because I can see many of them are not there.
Okay, I'll try to
All right.
include that app. There's
Yeah,
one
yeah,
app
do that.
the attendance can
Yeah.
be taken.
I know. You can do that. So that is a very important thing that we discussed today: the system call, the user mode, and the kernel mode. So summarizing, because most of you are not paying attention. So let me summarize quickly. The summary is that the operating system works in either of the two modes. One is the user mode, another one is the kernel mode. Now, all non-privileged instructions can be executed in the user mode. But whenever we encounter a privileged instruction means the instructions which lead to accesses to shared resources. Then we have to, the operating system will have to switch to the kernel mode. And how is that done? Whenever a privileged instruction is encountered by the CPU, a bit is set. And when the program counter sees that bit, then automatically an interrupt is generated. And not only that bit is set, but also a parameter is set. Now with that parameter, depending on open file or print or whatever, it comes to the kernel. And in the kernel, there are several programs. A number of programs are there for different services. There is some program here, some program here. Oh, again, I have not shared. In the kernel, there are several different programs are there for different services. Now, the kernel has been entered with some particular request, say P. Based on that, the program that is servicing P is accessed. And only one process can access the kernel at a time. After that is done, we go back to the user mode. All right. Now, this system call also reminds us, and very rightly so, about the concept that you have already studied, and that is interrupt. Now, interrupts can be of two types: hardware interrupts or software interrupts. Now, hardware interrupts are generated by whom? Mohit Agarwal. Devayito, are you still there?
Yes, sir.
So tell me, hardware interrupts are generated by whom?
Hello.
Hello.
Yes, sir. Hardware interrupts could be generated by input devices or
Only input devices.
so
Output
whenever
device also. Any other.
yes, IO devices.
Any IO device
Yes.
can generate a hardware interrupt. When is that hardware interrupt generated? Let me ask. Martand, are you there? Subrata Martand is absent. Ovirup Majumdar, are you there?
Yes, sir. Yes, sir.
Message? Okay.
Yes,
so
sir.
now Martand is there. Yes, Martand, tell me that what was the question? What question they asked?
It's a hardware interrupts.
Hardware interrupts what? When do hardware interrupts take place? Can take place? Martand. Ovidup Majumdar.
Yes, sir. Yes, sir.
When can hardware interrupts take place?
Hardware interrupt takes place when we need to access any hardware.
Who interrupts whom? Well, we have to go to the fundamentals. Say, I have got the CPU here.
Yes, sir.
There's something fundamentally wrong here. I have got the CPU here. And I have got some IO device here. Now, who interrupts whom? I'll draw an arrow. Tell me. The arrow should go from whom to whom?
So CPU to IO device. No, sorry. IO to CPU.
CPU to IO device. Huh?
CPU to IO device.
This is a lottery. Tossing a coin or what?
CPU to IO device.
CPU to IO device. Anybody else?
Sir, the hardware interrupt is generated when the process assigned to the hardware is completed.
Sir, I don't want to go that far. I am stuck much before. Who is in this diagram? CPU and IO. Who is interrupting whom?
Sir, IO is interrupting CPU.
Yes, sir.
Yes. The IO interrupts the CPU. Right? Whenever it needs a service, or whenever, suppose it was doing something, its job is done over, wherever. The CPU is interrupted and the IO or the other devices interrupt. Okay? This is a fundamental thing. So there is no scope of confusion over here. So IO, the CPU is interrupted. Somebody who is working is interrupted. All right. Say in a bank teller, you are doing something and somebody comes and knocks, say, I need some money. So you are interrupted. Similarly, CPU was doing something and is interrupted. Now then my question comes, when do you think hardware interrupt can come? Hardware interrupt is asynchronous. You understand the meaning of this? Asynchronous. What do you mean by asynchronous? Asynchronous means it can come at any point of time. Any point of time. I do not know. Suppose another simple case that there's a health monitoring system and the CPU is here and there's a patient lying here and some monitoring device is connected here, and whenever there is an alarm situation, that will generate a signal to the CPU, so that the CPU immediately sets up an alarm or calls the doctor or whatever. So that can come at any point of time. That is why that is asynchronous. On the other hand, software interrupts are interrupts which are software interrupts are interrupts which are written within the program. So there are some lines of code and there are some software interrupt generating codes written here. So as many times I run this program, the interrupt, software interrupt will occur at the same time. That is, software interrupts are synchronous. That means as many times as you do it, it will run at the same, it will occur at the same time. Similarly, so here say P1. P1 was executing and here there is a printf statement. Here there is a printf statement. And whenever there is the printf statement is encountered, I'll have a system call, and that system call is nothing but a software interrupt. Okay? So just like hardware interrupts, this software interrupts are responsible for generating the system call. And just as you have learnt about interrupt service routines, that whenever a particular system call, that means a system call, says something, I think Shubhrato will talk about that. Unix gives you a interrupt generating statement signal with some parameters. Like say kill -9. I'm not going into all those. So there are different interrupt generating instructions in Unix. If you give that, all right, if you give that parameter here, then a software interrupt will be generated from the user mode to the kernel mode through that software interrupt, and the parameters will guide me to the basic required kernel module, which may be a file handling module, which may be a device driver, it can be anything. But the core point is it must be dealing with some resource that cannot be shared. And just to, now I'm introducing I'll conclude with this term, just to ensure that the access to a shared resource is mutually excluded. That means more than one cannot access it at the same time, are mutually excluded. Okay, we take resort to the kernel mode of operation. Now, mutual exclusion we'll see much more, but right now, so summarizing, today we have learnt about the necessity of two modes of OS. System call, generation via software interrupts. So please study this part before we proceed further in the next week. Thank you. Any questions? Any questions from any one of you?
So I'm switching off the recording.
Yes.